Hello, this is Dr. Hisham Said. Welcome to this video. We'll learn about 2D equilibrium in beams. And we have an example here of this beam AB. And beam AB here is supported by a pen at A and a roller at B. But the roller here is supported on an inclined surface with an angle of 30 degrees with the horizontal line. And the beam here is carrying two loads, a point force 2 kilonewton and a point moment 2.4 kilonewton meter. And we need here to draw the free body diagram and also to calculate the support reactions of the beam. So if I draw the free body diagram here, I'm drawing kind of copying what's in the figure but focusing on what is important for to show in a free body diagram. So the body itself, dimensions, the loads. And then I didn't draw here the supports because I will replace them with the reactions for each one. So the pen at A, I have here two reactions, AX and AY. And then for the roller, I have a single support, only one, which is perpendicular to the surface where the roller moves, on which the roller moves here. So I call this support BR, or the reaction at B. And you can see here that we have three unknowns, two reactions at A and one reaction at B. And as a 2D equilibrium example, the general case, which is the non-concurrent equilibrium, or non-concurrent force systems, I have three equilibrium equations. Sum of forces in X, sum of forces in Y, and sum of the moments around any point would equal to 0. So if I apply each one of them, because I have three equilibrium equations, I will be able to solve for the three unknowns I have. So if I do the sum of forces in X, so I have AX going to the right, which is my positive direction. And then the X component of BR goes to the left, and with just some trigonometry here, I see that it has 30 degrees with the vertical line. So this means that the horizontal component will be sine 30 BR. So I have two unknowns in one equation. I can't solve for any one of them, so I have to do the second equilibrium equation, which is sum of forces in Y. So I have here AY going up, which is positive, and then the load 2 kilonewton, and then the vertical component of BR, which is also going upwards. Pay attention here that the moment, the point moment load of 2.4 kilonewton meter is not represented in the sum of forces in X or Y, because that's a moment. So it will show up when I do the sum of the moments. So far it's not showing up. So now when I try to apply the sum of the moments, the question here is around which point. So you have to pick a point to apply the sum of the moments. Unlike the sum of forces, you have a direction to focus on, but here it's the sum of moments around a point. So my recommendation here is to pick a point that will result in the least number of unknowns in that moment equation. So that's kind of the art here, is to apply it in a point that eliminates the impact or the contribution of the unknowns I have toward the moments around that point. So if I apply the sum of the moments around B, I'm eliminating the moment from both the BR and AX because both of them are going through B. Or I can also apply the sum of the moments around A, so I'm canceling here the moments from AX or AY because they're going through A. So either one of these sum of moments, of course I can apply sum of moments at any point of space, but now I'm not canceling anything, right? I'm not canceling any of the unknowns I have. So it's either A or B, and both of them are canceling the same number of unknowns. So either one, it's actually up to you. So for me, I have the notes based on the sum of moments around B. I recommend that you also do the sum of moments around A and check the result if you end up with the same result that I will get here. So sum of moments around B is equal to 0. So canceling BR and AX, so I'm left with AY. So AY will be multiplied by the distance from A to B, the moment arm 1.6 meter, and then I have also the point load 2 kilonewton multiplied by the moment arm of 1.2 meter, which is 0.8 plus 0.4 meters, and then the point moment load here 2.4 kilonewton meter. I don't multiply by a distance because it's already a moment. It's not a force that needs a moment arm to create a moment. So now I have a third equation, and I'm lucky here. I have only one unknown. I will solve for that unknown, and you can see here that AY is actually equal to 0. That's interesting. Let's think about it. So the if I take the moment around B, you can see here the point moment, the 2.4 kilonewton moment, per kilonewton meter moment, that goes clockwise around B, but the 2 kilonewton force with the moment arm of 1.2 meters from B causes a counterclockwise moment, and these two are equal. So kind of the point moment 2.4 kilonewton meter tries to lift the beam up, but then the load with at a distance of 1.2 meter moment arm tries to rotate it down. So at the end they cancel each other, and you don't really need the support reaction AY to resist the rotation of the beam here, because you don't have a rotation of the beam. It's just the loads are actually helping by canceling each other's rotation around B. Again, around B. I'm focusing here with the moment around B. So I'm done with the third equation, third unknown. So now I can go back to the equations. So specifically equation 2, I can plug in AY is equal to 0, and I will end up here with the reaction at B equal to 2.3 kilonewton, and then plugging now this value into the first equation to end up with AX equaling the horizontal component of BR, but going to the right in this case, and I will end up with 1.15 kilonewton. And you can see here all the answers, or mainly the two unknowns that I have values here, they ended up with positive values. So that confirms that the directions of the reactions that I assume, because at the beginning I didn't know if AX goes to the right or the left, so I actually didn't mention that, but I just assumed directions of all these reactions. And then at the end I checked that all the values I got for these unknowns are positive, so that confirms that the directions are correct. So that's the end of this video. I got all the unknowns that I want, and I drew the free body diagram, so I satisfied the requirements of this problem. Thanks for watching, and take care of yourself and those around you.